Okay, but I'll try and record later and post on the website. That way, it's just there forever if we need it. But I guess I'll record something just myself without all of you because the website's technically publicly available. Um, so good, Luciano. Good.
Yeah, that's good.
Okay. All right. So again, kind of plan is just wanted to give a basic introduction to performing solvation free energy calculations, so that we can understand how the black box works, right? And to then give you some insight in terms of when we set up the calculations, why we're just not directly performing free energy calculations on your partially miscible system. Okay. So goal is, right, is to get a basic understanding of how these calculations work, so we can understand how the black box works, so that we can follow along and see why we're performing the calculations the way we are, and then also appreciating, what that value is that we get from our solvation for energy calculations. Okay. All right, and so again, I'll post these online. I'll embed them in the website, and so that there's even a link back to the website and link to OSC as well. And then tonight I'll try and record myself going through the notes as well, so I could post that screencast on the website, just so you have it as a reference. Okay. But remember, we'll talk briefly over these next couple of days. If you ever need anything, just send me an email, let me know, and I'll do what I can to help you out. All right. And so basic outline again is plan for today is we're just going to give a very basic introduction to the theory of solvation for energy calculations. And then the plan would be to, what I have listed as equilibrate our systems, but do the first part of setting up our solvation for energy calculations. So we'll equilibrate so that we can come back tomorrow. We'll complete our discussion talking about applications of solvation for energy calculations, but then actually submit our calculations, which will then come back on the 18th and analyze. All right. So basic picture. So when we talk about solvation free energies, right? So conceptually, what we're going to look at is we're going to look at the change in free energy, Gibbs free energy, molar Gibbs free energy, of taking some solute, which I'm labeling here as component 1, from a non-interacting ideal gas state, right? And so the Gibbs free energy between this non-interacting ideal gas state and the Gibbs free energy of that solute interacting in some solvent phase. Okay. So solvation free energy is the Gibbs free energy of transfer of taking the solute from a non-interacting ideal gas state to solution. So Gibbs free energy is solvation, or solvation free energy is this change in Gibbs free energy. So how we physically model this in our simulations, though, is if I look at this reference state, right, in a matter of notation as well, this reference state here, my ideal gas state, right, I'm typically going to refer to as 0. And then the state in which my solute's fully interacting in solution, I'll call that my target state, and we'll often label it as state M, right? And it's ultimately going to depend on how many of these stages we have. Okay, but I've got my reference state is an ideal gas, and my target state is my solute fully interacting in solution. So when I think about my reference state, okay, what is my reference state? My reference state is the solute in an ideal gas phase, right? What is an ideal gas? Right? So an ideal gas is a system in which molecules don't interact and they don't take up space. So in an ideal gas, molecules don't interact and they don't take up space. So how we, model this ideal gas phase in reality when we're actually performing our solvation for energies calculations is we're going to set up our calculations so that our reference state, right, where we have our solute in a non-interacting ideal gas state, right? So I'm going to depict my target or reference state as this, right? And what I have here is what we do in our simulation is this is going to be, say, our system, right, in which we have our solute and our solvent, but we're going to turn off all of the intermolecular interactions between our solute and the solvent. So how we model this ideal gas reference state, right, is we take our solute. Okay, so we're going to have a system in which we have solvent molecules and we have our solute molecule, but we're going to turn off the intermolecular interactions between the solute and solvent. Okay. Now remember, we said an ideal gas is a system in which the molecules don't interact and they don't take up space. Okay, so when I turn off the intermolecular interactions between my solute and my solvent, okay, well, for from the perspective of component one, well, I'm in a non-interacting ideal gas state, right? Component one can be found at any location in the simulation box with equal probability, right? It's not interacting with anything, right? It's not interacting, right? And it's not taking up space in that it's the only molecule in the box, and it can be found anywhere in that box with equal probability. So when I think about solvation free energy, right, up top, right, this is the theoretical picture that I might see in a textbook. How we model it is we model it as such, right? We capture this non-interacting ideal gas state by modeling the system in which your solute is not interacting with any of my solvent molecules. Okay. So from the perspective of component one, my solute, it's in a non-interacting ideal gas state in that it's not interacting with anything. It can be found anywhere in my system with equal probability, right? It's not occupying space. Okay, now in part of this then is my reference state is the state in which I have a solute and I've turned off the intermolecular interactions with my solvent molecules. And then I have my target state here, right? Now my target state only differs in that now the solute's interacting with the solvent. Okay. So how we get from our reference state to our target state, or the difference between them, is here solute solvent interactions are turned off and here they're turned on. Okay. So my solvation free energy, right, is going to result from, turning on the intermolecular interactions between my solute and solvent molecules. Cool. Now, in doing so as well, okay, when we define solvation free energies, there's lots of different conventions or methods for how we define solvation free energy. So the standard convention that we adopt when we're performing molecular simulations is we say that our transfer is going to be performed at a constant molar density or constant molar concentration. Okay, so what does that mean? So what that means is when I look at my reference state and my target state, okay, the idea is going to be I have some large number of solvent molecules and I have one solute molecule in which I'm turning the interactions of that solute and solvent on and off. Okay. So I'm going to have, say, 1,000 solvent molecules and one solute that's not interacting with the solvent. Then I'm going to have 1,000 solvent molecules and one solute molecule interacting with the solvent molecules. Okay. So the idea is going to be is that in my reference state and in my target state, the molar volume, right, or you could just think of the total volume in a simulation box, right? The volume of these two boxes are going to be very similar. They're going to be approximately the same. Okay. So if we assume that the volumes of the two boxes are approximately the same, okay, well then the molar concentration, right, of my solute, right, in my reference state is, one solute per, volume of that box. And in my target state, right, I still have just one solute, right, in that volume of the box. Okay. And so what we assume is we assume that that molar concentration, so essentially the volume of those two boxes, are approximately the same. Okay. And so this is just a convention when you compare to reference data, is when they report solvation free energies. Typically, they'll list a convention with how they're defining that ideal gas state. All right. And the most common one that we see is that they're looking at transfer at constant molar density, although others can be used. All right, so here's my picture, right, of how we're defining solvation free energy in our simulation box, right, and this is the theoretical process that we're modeling. All right, so now the key of performing these is, my discussion is going to be limited to perturbation based methods to predict solvation free energy, because that's what we'll perform. But there are other techniques out there, right, which are similar, but different in the derivation beyond kind of these first couple of lines that we put up here. So the key to performing a solvation free energy, of how we're going to calculate the solvation free energy, is to start with our statistical mechanical bridge function, right? So our bridge function is just that, the relevant free energy. So if I'm in an NPT ensemble, right, the relevant free energy is my Gibbs free energy. So I have my dimensionless Gibbs free energy is equal to the negative log of my partition coefficient for the relevant ensemble. Okay, so my dimensionless Gibbs free energy is equal to the negative log of my NPT partition function. Cool. So now when I think about salvation free energy, okay, so my salvation free energy is going to be equal to, this is my dimensionless salvation free energy. This is the dimensionless Gibbs free energy of my target state relative to my reference state. Okay. So I've got the Gibbs free energy of my target relative to my reference. Okay, where if I apply my bridge equation, that's the negative log of, here's my partition coefficient of my target state relative to my reference state. Now, when I think about my partition functions, right, I could break my partition function up into my momentum integral and my configurational integral, right? Configurational integral is what I'm going to designate by here with Z, which is common. Like the Quarry's textbook was the book that I used in terms of learning statistical mechanics. Okay, but I could take my partition function and I could break it up into my configurational integral and my momentum integral. Now, the momentum integrals are going to be exactly the same, right? My momentum integrals are going to be exactly the same, is because my target state and reference state, they contain the same molecules, right? So when I look at how I model it, right, this is in part why we model it like this. When I look at my target state, right, it could have, say, 1,000 solvent molecules in one solute. Okay. My reference state, right, also contains 1,000 solvent molecules in one solute, right? It just differs in that in this case, my solute's not interacting with my solvent. Okay. But one of the fundamental, so you must have talked about it with Luciano, is one of the fundamental assumptions in statistical mechanics, but then also fundamental to molecular simulations, is we assume that our momentum integrals and our configurational integrals are independent of each other, right? That my momentum's independent of position and my position's independent of my momentum. Okay, so we assume that our momentum integrals and our configurational integrals are decoupled, and then your momentum integral, right, just becomes the corresponding momentum integral of an ideal gas. So the momentum integrals for my target state and reference state are exactly the same, and so they would cancel out. So I'm just left with the negative log ratio of configurational integrals. Okay. And the that issue with the momentum integral was one that took me a while, I remember, to wrestle with as a grad student. But that's also the basis of why we can perform, either Monte Carlo simulations or molecular dynamics to sample configurational phase space, right? Both will give us the same results, um, but that's an aside. Okay. So my salvation free energy then is going to be equal to the negative log ratio of the configurational integral in my target state relative to my reference state. Now, in terms of, in general, my configurational integral in general, right, is equal to, this is the integral of the exponential of negative beta. So beta is 1 over kT times my Hamiltonian, which is a function of my three-dimensional position of every molecule or every atom and volume. Okay, so the integral over all of configurational and volume space, or my Hamiltonian is my potential, which is a function of position, plus PV for the case of an NPT ensemble. So, all right, salvation for energy is a negative log ratio of configurational integrals. Now, how we're going to go about calculating these configurational integrals. Now, I just yesterday had my exam for my thermodynamics class, my chemical engineering thermodynamics, and trick we use in setting up a lot of our expressions for fugacity. All right, the same as we have here. As I say, one of our favorite mathematical tricks is we've got the additive identity and the multiplicative identity. All right, the additive identity would be anything plus 0 is just that, anything you started with, right? And multiplicative is, anything times 1 is just that, anything you started with. So here we take advantage of our additive identity, where I'm going to take the Hamiltonian of my target state, state M, okay, and I'm going to add 0. So I'm going to write this as the Hamiltonian of my target state plus H naught minus H naught, right? Hamiltonian of my reference state minus Hamiltonian of my reference state. Rearranging, I can write this as H naught plus HM minus H naught, or the notation I'm going to use here is H naught plus delta H, where delta H is the change in Hamiltonian of my target relative to my reference state. Okay, so this, right, is already taking the form of, right, a perturbative type of expression, where I'm writing my property of interest, so my Hamiltonian and my target state, right, is equal to the Hamiltonian of my reference state plus some deviation or perturbation term. Okay, so my Hamiltonian in my reference state is equal to my reference state Hamiltonian plus my deviation term. So if I put it all together now, okay, so what I mean by put it all together is here's the Hamiltonian of state M. Okay, all right, I'm going to plug that in to my definition of my configurational integral up there in state N. Okay, so putting it all together, my solvation free energy, we said was the negative log ratio of configurational integrals of my target relative to my reference state. For my reference state, I'm just going to keep it as Z naught for now. Okay, but for my target state, I'm going to start by plugging in e to the negative beta. Here's the Hamiltonian of my target state times. So integrating over all position and volume space. What I'm going to do next is if I'm going to plug in my perturbation expression, which I had up here. So HM, right, is equivalent to H naught plus delta H. Okay. And so taking advantage of my rules of exponents, okay, this is equivalent to integral of e to the negative beta h, okay, delta h times e to the negative beta h naught, right? And then integrating over all of position and volume space. Rearranging slightly, okay, I'm going to pull out or just write out separately e to the negative beta delta h, okay? And then I'm going to group this together, right? I'm going to group 1 over z naught times e to the negative beta h naught. And why I'm going to group that, okay, is, this is e to the negative beta h naught. H naught's the Hamiltonian of my reference state. So this just becomes the probability, right, of observing a given configuration in my reference state. So I write that on the next line, right? That term, right, just becomes, right, so we've got this expression here. This term, okay, just becomes the probability of observing a given configuration within my reference state. So I'm going to call that P naught, and it's a function of position and volume. Okay, this is just the probability of observing a given configuration in my reference state. Okay? And so then finally, okay, what I get from this, right? So now I've got the integral of e to the negative beta delta h times P naught, the probability of observing a given configuration in my reference state, and then I'm integrating over all of configurational and volume space. Okay, well then this just becomes an expectation value. Okay, so this then is just equal to, right? I've got the negative log, which I've been neglecting. Okay, but then it's just an expectation value of e to the negative beta delta h um, within my reference state and within my reference state. Cool. And then all I do, in this last line, which we'll look at and emphasize, is that, how we're going to execute this. We'll talk about more how we're going to execute this. But, if I skip back to a picture, okay, is so, the idea here now is what I need to calculate is an ensemble average in state naught, right? So I'd perform a simulation and say state in my reference state. And then periodically I need to calculate, the probability of observing a change in Hamiltonian, right, within my reference state. So periodically I would say turn on my intermolecular interactions in state 0 and measure that change in e to the measure e to the negative beta delta h. Okay, but right, the comment here, since volume's constant, okay, so the volume's not changing when I perform this fictitious perturbation within state naught. Okay, well then my Hamiltonian, since volume's not changing, is just equal to change in internal energy, and I'm just dropping volume here, right, because it's only going to be a function of configuration then at that point. So my final working expression then is my solvation free energy is going to be equal to negative log times now the expectation value of e to the negative beta delta u, which is a function of position. And we're going to talk on the next slide about how we'll actually perform said calculations. But if you could follow along with what we just did, you could derive perturbation theory. Okay. So in practice, so essentially how this works then is the beauty it is now we have this expression for our salvation free energy, and all that we're left with is an ensemble average within state zero. Okay? So what I mean by this is, expectation value. So just like if I had, an expectation value of say the volume in state zero, what that would be is, me just tracking the volume, say as a function of time within my simulation, computing an average, right? And that'd be the expectation value then of my volume in state zero, right? So we're going to have an ensemble average in state zero, just as we would in that case. So in theory, right, what I would need to do here to compute my salvation free energy is in the traditional perturbation theory is I would set up a simulation within the state naught. Okay? I'll set up a simulation in the state naught in which I have all my solvent molecules. Then I have my solute that's not interacting with solution, with my solvent. Okay. All right. And now what I need to do is I need to compute an ensemble average of e to the negative beta delta U. Okay. So what is delta U? Delta U is the internal energy of my target state relative to my reference state. So what I do is I perform my simulation. Okay. So I set up my simulation. My solute's not interacting with my solvent, and it's running as normal. Then periodically, you can think of it as pausing my simulation. I'm going to compute the internal energy of my system. I'm then going to turn on the interactions between my solute and solvent, compute the internal energy of that system, compute the difference, which then allows me to compute this term. So I periodically pause my simulation, record the internal energy, record the internal energy of the system where I turn on the interactions between the solute and solvent, record that, and then at the end of the simulation, I'll be able to compute at each one of those points in which I sample, e to the negative beta delta U, and then I compute my expectation value, right, the average. And that's the idea, right? And the beauty of this is in order to compute the salvation free energy, I need only perform a simulation in my reference state, right? I don't actually need to perform a simulation in my target, right? The only simulation that's needed is one that's here in my reference state. I don't actually need to model, right, or do any sort of calculation in my target. Okay? Pretty amazing, right? Get the idea? Now, in theory, right, we could also work in the opposite direction, right? I'm trying to remember if I have it written down here. Okay, I don't have. So here we have this written down, right? Of I could go or I could model my target or reference state, um, and perform these fictitious perturbations to compute the change in energy between my target or reference and target for a given configuration. So I only perform a simulation in my reference state. You could also very well do the opposite, right? In which you only perform a simulation in your um, target state, right? And then periodically perform fictitious perturbations to your reference state. Right? And so you could work out an equivalent expression where you're performing, these ensemble averages in state one state M as compared to state one. Okay. But the key is you only need to perform a calculation in one of these states. Okay. Now, this is so I guess okay. I guess if I don't hear anything, I'll assume so far so good. Now, a topic that comes up a lot is this topic of phase space overlap, right? Phase space overlap. What am I trying to get at with phase space overlap? So if I look at, so sorry, I'm skipping around and going backwards, but if I look at kind of original expression for salvation free energy, right? It's a log ratio of configurational integrals, right? So it's our configurational integral of our target state and our reference state. Okay. Um, and so, how we get to the point that we have is we have this ratio of configurational integrals, and I'm applying perturbation theory essentially to my Hamiltonian of my target state, right? I'm taking the Hamiltonian of my target state, and that's what I'm writing as the Hamiltonian as my reference state plus, this perturbation or deviation term. And so, the idea of phase space overlap now is when we perform these calculations is, I'm sampling within my reference state, okay, but I'm a so what am I trying to say? So I'm sampling only from my reference state, Okay. And trying from the configurations that I generate or look at in my reference state, I'm trying to get an estimate of the configurational integral in my target state. So I'm only sampling in my reference state. Okay. And based on the configurations that I'm generating in my reference state, I'm trying to come up with an estimate of the configurational integral of my target state. And so, the idea behind phase space overlap then, or how it works, is if I would try and think in terms of pictures, okay, in state zero, okay, state zero, I have an ideal gas, right? So in an ideal gas state, my solute molecule could be found anywhere in the system with equal probability. So my solute can be found anywhere in the system with equal probability. Now think about my target state. Okay, my target state where my solute's fully interacting with my solvent. Okay, at the very least, what you can picture in your head is you are perfectly going to exclude regions of phase space in which your solute overlaps with your solvents at all. Okay, so the fact that your solute's interacting, it's going to have a more restricted phase space. Restricted phase space in that configurations such as ones in which my solute's overlapping with my solvent, right, aren't going to happen. They're prohibitive. So we can think of the phase space of my target, okay, state in this case, is actually a subset of my reference state. Because in my reference state, it can be found anywhere with equal probability, okay, but there's only some small number of those configurations which are actually, or small parts of that configurational phase space, which is actually accessible with my target state. Okay. And in a case like this, it's in part why these methods are rather inefficient. Okay, in that if I had a configuration like this in which my solute's overlapping at all with my solvent, okay, well, that's going to be prohibitive in my target state, right? So the probability of observing that state, it's going to be virtually zero. Okay, and so you run the risk of generating lots and lots of configurations, which essentially, contribute no weight into the configurational integral of that actual target state. Okay, but the beauty is that you need only perform a simulation in your reference state, right? Or you could do the equivalent in the target state. Okay, but in this case, you'd perform a simulation in your reference state, and then just based on that, you estimate the configurational integral in the target. Okay. Now, that comment of phase space overlap, though, in terms of just modeling the target state, to performing a simulation here and estimating, configurational integral of state zero, right, that one would actually be more challenging because now, this phase space is a subset of that. And so there'd be a lot of regions of phase space that you just wouldn't sample, right, that would be important to state zero. All right. So if you could follow along with that, right, you've just derived perturbation theory. Okay. Names typically attached to, traditional perturbation theory, as we just described, are Zwanzig's perturbation theory and Whittem, typically like Whittem insertion methods. And then I have a link here to a book that I like, in addition to the type notes which are posted on that website. Cool. All right. So then we'll move
That's
from there,
good.
and we'll kind of lead into, based on this, where we get to some more advanced methods. All right. So, our key feature of a perturbation theory method or perturbation type of approach is if I want to compute the solvation free energy, I need only perform a simulation into my reference state. I don't actually need to perform a simulation in my target, right? So I could set up this equation so that I perform simulations in, state zero and use that to estimate my configurational integral in state M. Or equivalently, I could set up a simulation in state M in which I use that to estimate the configurational integral of state zero. Okay, but the key is, okay, if I'm trying to compute the free energy difference between two states, these two states, I need only perform a simulation in one of those states. All right, so now that's going to lead us to what's called Bennett's acceptance ratio method. Okay, so the idea is, is again, if I want to compute the change in free energy between two states, I need only perform a simulation in one of these states. I can perform a simulation just in state zero, right, and use that to estimate the configurational integral in state M. So the idea behind bar now is, well, if I want to compute the free energy difference between state 0 and state m, okay, what I'm going to do is I'm going to create some intermediate state, which I call here m prime. And so the key then is I can perform a simulation just in state 0, okay, and calculate the free energy difference between state 0 and m prime, okay. And then I could also go in the opposite direction, and I could perform a simulation in state m, okay, and calculate the free energy difference between state m and m prime. Okay. Now, what's special about m prime, okay, is this is some intermediate state, but the intermediate state, I don't actually need to perform a simulation, right, or perform any calculations within the actual intermediate state. Okay. The idea being, again, if I want the free energy difference between two states, I need only perform a simulation, right, or generate configurations in one of them, right? So it could be state 0, then between m and m prime could just be state m. So I don't actually need to model, right, or perform any simulations in state m. So the idea is, well, if I compute the free energy difference between 0 and m prime, right, and m prime and m, the sum of the two of those gives me the free energy difference between 0 and m. Okay. So my solvation free energy, which is the free energy of state m minus my reference state, right, I could break it up into a sum of two differences. All right, so this term's difference in m and m prime, and then this one's the difference between m prime and 0. So cool, right? So I could perform, free energy calculation in state 0 and m, and estimate the difference between 0 and m prime and m and 0 prime, and add them up. Okay. Cool. Now the idea behind Bennett's method is, okay, I can see this in principle, right, and how this would be beneficial. All right, so add an intermediate state would mean I have a smaller deviation or perturbation between, 0 and m is going to be a smaller perturbation than 0 to big M, right? And m prime to m is going to be a smaller perturbation than from, again, 0 to m. Now, the realization that Bennett had, though, is, well, what is pretty cool is I don't actually need to perform a simulation in state m prime. So the idea behind Bennett then was, well, can I, you know, perform some simulation in 0 and m, okay, track, these fictitious perturbations as a function of time, okay, but can I say optimize or, find the optimal value of m prime, which would be a scaling between my solute and solvent intermolecular interactions? Can I find the optimal, value of m prime, right, or scaling of those intermolecular interactions after the simulation is complete, right? And could I find the optimal, value of m prime scaling so that I optimize the phase space overlap between those neighboring states? Okay, and the idea behind, you know, um, optimizing phase space overlap is, well, you're going to minimize, right, the uncertainty in your estimate. Why? Because more of those configurations that you're generating or sampling in your reference state are actually going to be of importance for your target state. Okay, so that was the idea behind Bennett, and so he was a much smarter person than I was, or I am, and so he actually performed an optimization process in which he's performing a simulation state 0, a simulation state m, performing these fictitious perturbations to this intermediate state m prime. Okay, and what he was able to work out is he was essentially able to solve for the optimal value of m prime to minimize the variance or uncertainty in his calculations. And so, we need not go through the optimization or anything like that, but he, works out an expression for the solvation free energy just based off of an ensemble average in state 0 and state m. Okay, where now my exponentials have been replaced with, okay, f corresponds to this Fermi-Dirac function. Okay, so f of x is 1 over 1 plus e to the bx. And so if I look at this top term, it'd be my internal energy in state m relative to state 0 minus c, where c is a constant. And how I find for the constant is post simulation, I perform, this optimization. So I find the value of c so that the difference, if I'm summing over all of the states sampled, so that this minus that is as close to 0 as possible. But biggest idea behind Bennett is the idea is if I, were to introduce an intermediate state, I could perform simulations in just state 0 and just state m, okay, and estimate the free energy difference between 0 and m prime, okay, and m prime and m, without ever actually needing to model state m prime. So the idea is well, can I find the optimal value of m prime post simulation, right, after performing simulations in 0 and m and computing my properties of interest? Okay, and so that's Bennett's acceptance ratio method, named after Charles Bennett. Now, Bennett attempts to do two things, right? So what's being done with Bennett's acceptance ratio method is, one, we're thinking about these principles of phase-space overlap. Okay, and phase-space overlap again is if I go back to this picture, all right, I'm performing a simulation just in state 0. So I'm generating configurations, right, that follow the configurational integral of my reference state. Okay, it may be that a lot of those configurations that I generate that are value in state 0, right, are not of value in state m. Okay, so what I need to make sure is that when I'm performing my simulation in state 0, is that I sample all of the important configurational phase space of state 0 and of state m. Right, I need to make sure I'm sampling all of the important configurational space of state m, so that I'm able to accurately estimate its configurational integral. Now, these states in which solutes overlapping with solvent, right, they're just going to end up having zero probability in my target state and not actually contribute to the property of interest that I'm trying to compute. Okay. So with Bennett, one thing that we get out of this is you're going to increase the degree of phase space overlap between my neighboring states. Okay. So M prime is some intermediate state. So it's not quite going from non-interacting to fully interacting, right? It's going to be, say a weakly interacting solute. Okay. And so by, adding this intermediate state, the degree of overlap, right, or the number of, mutual states, or that, states that would be of interest to both systems, right, are going to increase. Okay. And then same thing going from M prime to M as well. Okay, so we're getting an increase in phase space overlap, and then the second thing that Bennett does is he performs this optimization, and so the functional form results from minimizing the uncertainty in the calculations. So that's Bennett. Okay, now so we said that the second thing Bennett did, or first thing he did, was he was trying to increase phase space overlap. Okay, now if you take that to a whole nother level, okay, this brings us to the concept of stratification. Okay, so stratification, the person attributed with stratification is John Vallot. All right, so the idea here being is that if I want to calculate the change in free energy, right, going from our reference state to target state, so here is 0 to m, okay, in the original perturbation expression, I perform a simulation and stay just in state 0 and use that to try and estimate my configurational integral of my target state. All right, so now the idea behind stratification, right, or so sorry, I'm getting ahead of myself. So that was first perturbation theory. Bennett introduced an intermediate state. So the idea being that if I compute the difference between 0 and m prime, then m prime and 1, right, I could sum the two of them together to give me the free energy difference between state m and 0. Right. Key being that my solvation free energy, just like my free energy, is a state function. Okay. So it doesn't matter which path I take to get from 0 to m, the value of m, right, and 0, or the value of m relative to 0, will be the same regardless of how I get from 0 to m. So stratification just takes it to a whole new level. And the idea is just that I can, add any number of intermediate states to go from state 0 to m. Okay. And if I had, this setup where I have 0, 1, 2, and then m, is I could compute the free energy difference between 0 and 1. I could compute the free energy difference between 1 and 2. I could compute the free energy difference between 2 and m. And if I add those all up, right, that's the same as the free energy difference between state 0 and m. All right, my solvation free energy, my free energy is a state function. Okay, so it doesn't matter how I get from 0 to m. Okay. So stratification, the idea is I can break up the calculation into a number of steps. Okay, and what stratification does for us, right, is it's going to allow us to increase the phase space overlap between those neighboring states. Okay, so the deviation, right, of perturbation and going from 0 to 1, right, is going to be a lot smaller than, say, from going from 0 to m. So I can add any number of intermediate states with the goal of trying to increase my phase space overlap. And now, if I'm performing, stratification, so if I just think about perturbation theory, right? And so what I mean by that is just performing my simulation in state 0 and trying to estimate, m, okay, as compared to bar. Okay. Well, if I want to, use stratification with perturbation theory, I'd perform a simulation in state 0, 1, 2, right? The only one I wouldn't need to perform a calculation in is state m. So, what I'm, writing here is I would need to perform n minus 1 simulations, right? N minus 1, simulations to calculate the n minus 1 differences in free energy to estimate the value in going from 0 to m. Okay. Now, if I were to use bar, okay, now what would happen is, bar would just give me further stratification essentially, in that if I perform a simulation in 0 and 1, right, I could solve for some optimal intermediate state, between 0 and 1 without actually modeling it. Okay, so I do the same thing for 1 and 2 and 2 and m. Okay. So the key is going to be where perturbation theory requires n minus 1 simulations, right? With stratification, bar requires n. Okay. And why I say that is it's kind of interesting and fascinating in the history of things. Okay. So for the longest time, how people computed solvation free energies, right, was just using perturbation theory, right, or Whittem insertion. Okay. So this was kind of the standard de facto method for a while. There were several papers that came out, including Barr's himself, right, that said, hey, bar is, a lot better, right? The accuracy of using bar compared to perturbation theory, right, is a lot better, right? There's a huge improvement in going from this to this. The problem was, though, is that people didn't do it, right? And why? Is because this calculation required one calculation, okay? Using bar required two, right? So bar doubled the computational cost to perform a free energy calculation. Okay, so bar required twice the amount of CPU time. Now, where bar has gained ground, though, all right, or has become more widely, used or adopted, is when I have larger molecules, it's inevitable that you need to use stratification. Okay, so, back in the day, if I was looking at, solvation free energy of Leonard-Jones molecules, okay, perturbation theory is okay. But as molecules get larger and larger, stratification becomes necessary. Right? And so now the difference, right, of needing n minus 1 calculations for perturbation theory to just n with Bennett, right, the difference becomes essentially insignificant. Right? I need one additional simulation, but with that one additional simulation, I get a huge improvement in my accuracy. Okay? So let me skip over because I thought I heard. Did someone have a question, Luciano? Or you've got your hand up?
Yeah, yeah.
So
If you can keep this slide, I'd
I'll
like
keep this
to,
here, Luciano, and can you ask all the questions if anybody else has one too? Because I can't
you
see
know,
both screens.
can you hear me? Okay, that's good.
Yeah.
Yeah. I'd like to ask you and use this slide, maybe this one and the last slide as well, to explain, especially for the students here, because I guess in this class only, I guess Marcelo and Alexandre actually um, have some ideas about difference between the methods for calculating the free energy.
Right.
And when you mentioned about the perturbation theory, you are talking about FEP, okay, FEP method, okay, FEP.
Yes.
And when you're talking about bar method, you're talking about the thermodynamic integration method, okay?
No. No.
No?
So Bennett's acceptance ratio method is a free energy perturbation method, right? They're both in the same family.
Okay. And what do you say about the M bar?
So okay, so Luciano's asking what's the difference between bar and M bar, is that right?
Yeah. because MVAR is exactly can be included in thermodynamic integration methods. Okay.
So no, thermodynamic
No,
integration fundamentally different.
completely different.
Yeah, you compute. So you're computing the same property, right? In terms of
No,
computing
yeah, of
a
course.
salvation free energy, right? The difference is you would set up a stratification process just like this, but what you're trying to estimate or what you're recording is the rate of change. So you're trying to estimate the change in your Hamiltonian with respect to, right, a change in lambda, where lambda would just be an S. So lambda would just be used to quantify, right, the scaling of these, intermolecular interactions in your system. So the idea behind thermodynamic integration is you're trying to estimate, or you're estimating the change in your Hamiltonian, with respect to a change in lambda. So you're estimating delta Hamiltonian divided by delta lambda,
Yeah, and then
which
and
the
then
limit that
and then
delta lambda
and
goes to zero, right, becomes an exact differential. But then you're going to integrate that, right? You'll use an appropriate
yeah,
method
you need to
to
integrate over
numerically
the
integrate
the,
that
the
expression.
states between lambda 0 and lambda 1.
That's right.
So it wouldn't be this like this process that it's occurring in bar, for example, because we are dividing the stages in different lambdas, different perturbation that we can do um, on the system. No,
So the difference is just fundamentally how you use the information, right? Um, so if I had this, right, with, I don't
yeah,
know, three
could
states,
be,
isn't very interesting, right? But
yeah,
the idea is I'm going to perform some simulation in state zero, okay? And so in state zero, right, I'm just computing this ensemble average of, so this is e to the negative beta u. So it's the e to the negative beta change in Hamiltonian. So I'm just computing this, right, within state zero. Okay, so within state zero, I'm performing my simulation. Periodically, I'm freezing my simulation, computing the energy with the interaction corresponding to state M, okay, relative to what I have in state zero. Okay, so I'm going to track that as a function of time. Okay, and then at the end of that simulation, however long I define it, I compute my ensemble average. Okay, and that gives me this change in free energy. Okay, cool. And then I do the same thing, right? I could perform a simulation to state M in theory. Okay, perform these fictitious perturbations to M, right? And I could compute, this, or estimate this change in free energy, and I add them both up. So if I'm doing thermodynamic integration, okay, then what am I going to do, right? So what I'm trying to do in thermodynamic integration is I'm trying to estimate, the change in Hamiltonian, so the change in internal energy, right? So I'm estimating the change in internal energy between, it, I'm losing words without drawing pictures. I'm trying to estimate the change in my Hamiltonian with respect to my change in lambda, but then I'm going to numerically integrate, right, that change, right, over a function of my states.
exactly. And then lambda is exactly changing the interaction energy between the species in the systems. Okay.
Right. So you're collecting the same data. It's how you're processing, applying, and using the data.
Mhm.
So bar, right, and then M bar, right, also fall into the perturbation bucket in terms of how they're using that information. The
And in
difference,
this sense, in this sense, what would be, for example, the difference between the bar, okay,
yeah.
and multiple stage M bar? Yeah,
So the difference between bar and M bar is just in terms of the amount of data that's collected and how it's used. Okay, so if I just have this picture here, okay, so what I would ideally like visualize, right, in terms of bar or even M bar, is essentially I'm creating this intermediate state between 0 and 1, 1 and 2, and then there's some intermediate state. I'll just call it between, say, 2 and M here. Okay, so in the bar picture, right, I have this intermediate state, and I'm going to perform a simulation in state 0. Okay, and I'm going to, so within state 0, I'm going to estimate the free energy difference between 0 and that intermediate state, which I don't actually model, right? I find post simulation. Okay. Okay. Likewise, I perform a simulation in 1, estimate the difference between 1 and that intermediate state, okay, which I find post-simulation. 1 in intermediate state, 2 in intermediate state, okay, 2 in intermediate
Yeah.
state, okay, M in intermediate state. But
And
in the
and
traditional,
what sorry, Andrew. In what it's changing, for example, between the stage one, two, three, and so on.
so in terms of state 0,
I'm asking this here exactly to clarify the idea to the students, because I guess would be interesting to understand, okay, what exactly we are changing in this in each stage about the interactions. So we can deal with, for example, the Lennard-Jones and Coulomb interactions between
right?
particles and the systems, okay? But in the same way, or we can vary the way to tend the van der Waals and Coulomb interactions in each stage. So uh, we can have kind of a pattern or reference protocol for each stage, or this depends on the systems we are studying, for example.
So if they go back to the first picture, right? So when I compute the change in or the solvation free energy, I've got the free energy difference between my target and my reference state. So my target state, right? So we have this, component 1, our solute in an ideal gas state. How we model that ideal gas state is we turn off the intermolecular interactions between the solute and solvent. So we have a state in which the solute is not interacting with the solvent. My target state, which I label state M here, right? That's the normal system that I think of, in which my solute is interacting with my solvent. Okay. So I have a state which is the same, only I turn off the pair interaction, the LJ interactions between my solute and solvent, and electrostatic interactions between my solute and solvent. I turn them off. Okay, where here they're turned on. So when we talk about stratification, or even in the case of Bennett, when I have these intermediate states, what I'm doing is I'm going to slowly scale on or turn on um, my intermolecular interactions. So rather than
Exactly.
going
And
directly from non-interacting to full, right, I'm going to
yeah,
slowly turn them on over a number of states.
yeah, in the practice, this turning of the van der Waals and Coulomb interactions between the species and the seasons, between the solute and solvent, for example, could be in the same way of that is like uh, we can change or turn off the interaction in each stage equally, or also we can change different in a different way, like we can start turning off the Lennard-Jones, and after that turning off the Coulomb, not at the same stage.
Right.
So
So
I'm looking at in the literature that people um, use different protocols depending on the situation, and this is like I'd like here actually to have your feedback, because as you have experienced for simulating many different solvents and solute and solvent, I don't know, have you tried some systematically changing about these two interactions between the species and the systems, and see what happens when we are turning off both interactions in a different way?
the answer is yes. But, so I kind of have something related to that here. So let me first comment about, you mentioned MBAR. Okay. So first, just to comment on this picture of MBAR versus bar is, so we said, in bar we have an intermediate state between, say, 0 and 1, right? But the key is I perform a simulation in 0 to estimate that perturbation. All right. I perform a simulation in 1 to estimate that perturbation. Okay. I have an intermediate state here. I perform a simulation in 1 to estimate that, and then 2 to estimate this, right? So the key is that I'm only trying to estimate that intermediate state by its neighboring subensembles. So the state between 0 and 1, right, I'm only estimating its value by performing this, simulation in 0 and 1 to estimate its value. So the idea behind MBAR is okay, I've got an intermediate state between 0 and 1, 1 and 2, 2 and m, is rather than just going from 0 to intermediate, 1 to intermediate, right? So essentially 0 to 1 and 1 to 0, I'm going to perform perturbations from 0, right, between 0 and every other state. So in M bar, I won't just perform a perturbation from 0 to 1 and then 1 to 0. Okay, I'll perform a perturbation between 0, 1, 0, 2, 0m. Okay, 1, 0, 1, 2, 1m, right, and so on and so forth. So what I'm going to do is I'm going to collect more information so that there's additional information I can bring into my optimization in terms of determining that optimal location of said intermediate state. So the only difference between bar and then M bar, right, where they call it multi-state Bennett's acceptance ratio, is the idea is they're generating more information, okay, and they're bringing more information into that optimization
Yeah,
procedure.
we are.
I
Yeah,
find
we're
that intermediate
increasing.
state.
Yeah, we are increasing the sampling as and also not only the sampling but the sampling between different states.
Right, exactly. And so did you talk about WAM at all in your workshop? Histogram reweighting? No, it. So so as an aside, so one of the persons whose names is typically attached to histogram reweighting is Alan Fehrenberg, and I met Alan. He's actually a faculty here at Miami, and he made an interesting comment in that when I first met him, I said, "Oh, you're famous. You're invented histogram reweighting and all this great stuff." And his comment was, "Well, not really, right? It was an idea that someone had 20 years before us. It's just they didn't have the computational resources, right, or ability to perform the calculation at that time. All right, we do or we did when I was, when we wrote our paper, right, and so, so it is, right. And so, in terms of M bar, they're not necessarily inventing anything new, right. It's just you know they're processing much more information and performing a much more detailed optimization, right, kind of beyond what Bennett did in 1976 on his limited resources. And it's very well for the problems of interest to Bennett, it may not have made a difference back at the time. Now, in terms of your, Luciano was asking about how we change your interactions, right? It becomes a game in terms of phase space overlap. And so, looking at our, multi-stage case, right? The goal is to try and, you know, have as much phase space overlap between our two states as interest. And so what I mean by phase space overlap is, I'm trying to estimate, say, the properties of this intermediate state just by sampling in state 0. Okay. So what I want to make sure is that, within state 0, right, I'm able to generate all of the important configurations, right, of interest for state that intermediate state, or even just thinking about going from 0 to 1 in the traditional perturbation approach. I need to make sure that I'm generating all of the important configurations, right, that state 1 needs, right, but from sampling within state 0. So the game is phase space overlap, right? I'm trying to increase the degree of overlap between my neighboring states. So in terms of how we typically set these up, right, or standard convention is that if I'm going from non-interacting to interacting, the first thing I'm going to do is I'm going to turn on my Leonard-Jones interactions. So essentially the first kind of goal, right, is I need to carve out my solvent cavity. Okay, so we carve out our solvent cavity by turning on our Leonard-Jones or dispersion interactions. Okay, so first I go from non-interacting to interacting just with Leonard-Jones, right? I'm carving out that cavity in solution. Okay. Then once that cavity is carved out and I have my solute interacting with my solvent via LJ interactions, then the next step is I turn on my electrostatic interactions. Okay. Um, General idea or convention is I don't turn on. Not I. It's not desirable to turn on Leonard-Jones and electrostatics at the same exact time. And the reason being is when you have very weak Leonard-Jones interactions, if you start turning on electrostatic, right? Electrostatic are very strong, right? They're Coulombic interactions. So you have these very strong long-range interactions. And so the challenge can be is if you just have a very weakly interact, or so the solute interacting with the solvent, and you have some very weak Leonard-Jones interactions, you can end up getting configurations which are, extremely close, right? And so when with electrostatic interactions, they end up creating these extremely high energies. So you can end up creating these really, unfavorable or undesirable configurations in your system. And so, how we stage things, right? The goal is to try and perform these calculations in such a way that we optimize, right, the degree of overlap between neighboring states. And then how you actually set it up, right, becomes.
Andrew, I guess, Andrew, sorry, I guess Alexandre can make
Excuse
answer.
me,
Yeah,
just
yeah,
a little question about the Leonard-Jones potential. You said that when you start to turn on the Leonard-Jones, you carve a cavity for the solute, okay?
yes,
But since the beginning of the simulation, the solute still have mass, right?
still has mass.
But
Yes,
just turning off the Leonard-Jones interactions, it allows the overlap between solvent and solute.
yes. So you mentioned mass, okay? So if I'm thinking about my configurational integral, right? So which is what I'm
Mm-hmm.
interested in, I don't care about mass, right? So mass only affects the momentum integral. And so if I were to perform a simulation of water, okay, in theory, if I model the oxygen as having a molecular weight of 16, or I model oxygen as having a molecular weight of 4, in theory, I'd compute the same exact configurational integral, right? So if you were to compute the, volume of that simulation box, if I were to compute the internal energy, it'd be exactly the same. Okay. The mass only affects the configurational integral, so it's going to affect your dynamic properties. It affects things like diffusion, viscosity, and things of that nature, right? And I guess might
Okay.
impact how you perform the simulation in terms of, maybe the time step that you need. But mass only affects your configurational integral. Okay? And mass is something people actually play with. So I wrote a paper once. Wait, did I? I'm trying to. No, no. But what I like when I've played with ionic liquids, challenge with modeling ionic liquids and performing solvation for energy calculations with ionic liquids, is they have really, really slow dynamics. And so a trick there to improve sampling is actually to decrease mass. So instead of having sulfur with a molecular weight of 32, you could decrease it to something like 12. And so the dynamics of the system speed up, but configurational integrals, thermodynamic properties don't change. But to
Okay.
your point of, carving out the cavity, right? It is, you know, so if I go from state 0 to 1, now let's just imagine I had a straight Leonard-Jones potential. Okay. So if I just took my LJ potential and I just multiplied my LJ potential by some scale factor, it's still, no matter how small that scale factor is. So even if state 1 is my, thousandth of my, full LJ potential, so 1 over 1,000 times my, intermolecular interaction, the phase space overlap, right, is still small, right? You still end up with, issues in terms of overlap between 0 and 1. So in fact, this is one of the hardest, differences in free energy to compute. So if I just use a straight up Leonard-Jones potential, the issue is that hard repulsive term. Okay, so that term that's 1 over r to the 12, even if I multiply it by a tiny number, it's still going to have the effect of infinity at short distances. And so the challenge is if I'm generating configurations in 0, okay, and I have, any configuration in which my solute's overlapping with my solvent, okay, well, that's going to end up, be causing an infinite energy within state, 1. And so that's going to have 0 probability, right, of actually occurring in state 1, right? It's going to be, it's not within, right, that important phase space of state 1. It's not going to actually contribute towards that configurational integral. And so what happens is you end up generating a lot of configurations in state 0, which have no value in state 1.
Mm-hmm.
Okay. And so, the trick that's, typically used is we apply what's called a soft core potential. Okay. And so what the soft core potential also essentially does is the challenge with the LJ is you have this term 1 over r to the 12, which is going to go to infinity at close distances, no matter how small that scale factor. So the LJ potential modifies, or the soft core potential modifies the LJ so that at small scale factors, it softens the shoulder. Okay. It softens the shoulder of my LJ potential. So rather than go to infinity, okay, it's going to go to finite concentrations at close distances. And so, what the soft core potential does is so the idea, going from 0 to m is free energy is a state function. So it doesn't matter how I get from 0 to m. So with the soft core potential, right, it at the low scale factors, it's going to soften the shoulder so that I can slowly turn on the intermolecular interactions. But if I have configurations in which the solute's overlapping the solvent with a small scale factor, right, those could actually exist with a small finite probability, right, within that, say, next neighboring state. And then with the soft core potential, as I scale up the LJ interactions, I, slowly make the repulsive term steeper and steeper. So it becomes more of a gradual process of essentially, making it so that I don't have solvents overlapping with solutes. And so then only once I'm, in that system in which I don't have any, overlapping configurations in which those are prohibitive, right? When I have my full LJ potential, then I turn on my electrostatic interactions, and I typically do that just in a linear fashion. And so I just turn those on, but I want to make sure that I don't have any overlapping configurations when I start to turn those on. And then, even in terms of, staging, how do you determine, how many stages to have, how gradual? Uh, that's a matter of trial and error, I suppose, for lack of a better word. And so even, part of the goal, kind of, interactions like this is when I was a grad student, right? There's lots of papers in which people perform, free energy calculations, and they describe things, and it always seems so easy. But the challenge is always actually executing, doing it in practice, right? And so, how do you come up with optimal staging? Well, trial and error, right? And so, the goal is to try and optimize the phase space overlap between your neighboring states, right? So electrostatics, those typically scale linear. Those aren't a problem. It's the LJ ones that could be problematic. And so, it might be that you find you need to add more systems or states to your system um, in order to get that to work. And Luciano, was there another comment in the or question in the chat?
Yeah, yeah. If possible, Andrew, can I share my screen to show you guys a graph?
Uh,
Maybe with this graph you can,
I think I got to come back here and
yeah,
share.
just
And I mean,
just a minute.
there's papers still. People are coming out and trying to optimize soft core potential.
Like
Um,
this, I guess this picture. Maybe you can use this picture to explain that. Like this. Can you see my screen?
so if you look at A, right? So A is looking at the case of I'm just taking my Leonard-Jones potential. So that yellow color, right? The last one is my full LJ. If I had a scale factor of 1. Okay. And the red is just taking that full LJ and multiplying it by scale factor of 1 times 10 to the negative 5. Right. And so the challenge is that it still has this repulsive core, right? So it's still going to infinity at close distances. Where on the right, if I look at your comment, right? So they're looking at a soft core potential. So what happens with the soft core potential is presumably they're using the same scale factors, is it actually softens the shoulder and then slowly builds up the shoulder as well. And so the challenge, with the full potential in A is if I were to go from non-interacting to, red, is that, if I'm having or I'm generating configurations in state 0, in which my solute and solvent are overlapping at all, they're going to be completely excluded. They're going to be perfectly excluded from that first state, which means they're going to have a probability of 0, So I'm generating a ton of configurations that don't actually contribute to my actual configurational integral. Okay.
Perfect.
And so then here, yeah, soft core, you would just build it up, right? So it becomes larger and larger and larger in terms of finite value until eventually there's no solute-solvent interactions that you would observe. Okay. And Gabby has tried doing some optimizations, but I don't know. But yeah, there's a lot of
Thank you, Andrew.
trial and
I
error
believe
question.
this can explain to the students, because the graph with the Lennard-Jones potentials can actually becomes the equation for soft core potential clearer than only the equation. I guess was amazing, your explanation.
All right, and I guess any other questions? And yeah, so typical approach is I think I'm sure. Yeah, so typical approach is we first turn on our LJ interactions. Okay, and we do that. You can see my screen, right, Luciano?
Yeah, we can see. That's good.
So we turn
Thank you.
on our LJ interactions first with one of those LJ potentials. So we, I say carve out my cavity, but I eliminate solute-solvent interactions within my system. And so I've got to push apart solvent molecules. I've got to separate solvent molecules to accommodate myself in solution. And then I turn on electrostatics. So LJ typically scale those with a soft core potential, linear scaling for electrostatic. Okay. And then the first bullet here that I have is kind of a subtlety, right? And so one thing that whenever I review a paper and it's not done, it's always one of the first things I pick on. But one of the challenges when I do this with MD, right? So again, I can use molecular dynamics or I could use Monte Carlo, right? Both are the same. They're just different techniques for um, estimating my configurational integral or sampling from my configurational integral. Okay, but with MD, where I need to be careful when I perform these free energy calculations is with respect to my thermostat. Okay. And so, I'm sure Luciano gave you a much better explanation when you talked about, molecular dynamic simulations. But in general, the picture I have in my head is we can use, global thermostats or local thermostats, right? And, the basic principle of all of these is, when I control the temperature is, if the temperature of my system is 290 K, I can generate a Maxwell-Boltzmann distribution for the molecules in my system, right? And the velocities of those molecules are going to follow distribution of velocities according to my Maxwell-Boltzmann distribution. Just the number of degrees of freedom would be n the number of molecules. Okay, I could do that on an atomistic basis, right? So I could calculate the velocity of all the atoms in my system. Okay, now the degrees of freedom is the number of atoms. And I could, plot the corresponding Maxwell-Boltzmann distribution, and it would, follow said appropriate distribution, right? And so, you can define right that temperature, compute that temperature in a number of different ways. Okay? And so, in terms of a global versus local thermostat, right? So you could think about trying to, so in a thermostat, I'm going to exchange heat between my system and surroundings, right? So that I can use that to, obtain right, a given temperature within my system, right? And I could exchange, heat on a molecule basis. I could exchange heat on an atomistic basis. Um, you know, should all be the same. Okay. So where we need to be careful, though, so in terms of controlling temperature, is when I'm in the state zero. So in state zero, okay, my solvent molecules are all interacting, but my solute is not interacting with the solvent. And so the challenge is that my solute isn't able to exchange energy with my solvent. Okay, so you could end up with a scenario in which you have. So again, this idea, if I have say 1,000 solvent molecules in one solute, I could have this scenario in which if I set the temperature to 298 Kelvin with a global thermostat, okay, well, the solvent molecules are able to interact with each other and exchange energy. Okay, and so if I were to look at the Maxwell-Boltzmann distribution of just the solvent molecules, it would look good. Okay, but I could end up with really hot, right? For lack of a better word, I could end up with a hot solute. Okay, because that solute, right, might have some high kinetic energy, and it's not able to exchange energy with my solvent. And if I'm not properly thermostating it, right, I could end up with this hot solute, which then would end up sampling conformational space not right at that desired or specified temperature. And so we need to make sure that we're applying local thermostats. Okay? And so local thermostats are going to have exchange of heat between our bath and every single atom within our system. Okay? So I need to make sure I'm applying local thermostats to ensure that I'm regulating the temperature of our decoupled and nearly decoupled solute molecules in our system. If you just apply no-say Hoover, all right, you could end up with issues where the temperature of your solute is out of control. All right, and so I just wanted to look at say 2 pictures. Yeah, and so in comment here is a lot of it is. So when I've taught this workshop before in a couple of places, right? And again, part of this is part of the reason for us going through and exercise together and going through it is I still remember as a grad student reading papers and okay, it makes sense, I can do that, but then actually doing it right is much different. And you know, I think part of it is like a lot of when it comes to free energy calculations, there's a lot of heuristics or things that people just do based on experience, right? And you know even down to how we stage trying to optimize phase space overlap in terms of how long do we run for, right? How many unique configurations do I have? And I mean, MBAR's gotten a lot better in that they offer suggestions, but there are a lot of heuristics kind of built in. All right, so just want to look at a couple of pictures, and then we'll be all set to be able to set up and equilibrate some calculations. And so again, the picture when we perform a salvation free energy calculation, so I'm calculating a free energy between some solute and a non-interacting ideal gas fate, and then the solute in solution. So the change in Gibbs free energy going from non-interacting to interacting. And so sometimes I like to say that this change in Gibbs free energy results from solute solvent interactions. Right, it's the effect of turning on my interactions between my solute and solvent. So just a couple of applications, just pictures, and we'll talk more next class. Is common way or common place where these are used is calculating things like partition coefficients. And the general idea is if I perform a salvation free energy calculation to keep the free energy difference between my solute in a non-interacting ideal gas state, right, and fully interacting solution, right, call that solvent 1. I could perform the same calculation and say some solvent 2. And so if I have this salvation free energy and this salvation free energy, right, key is they have the same reference state, which is just the solute in a non-interacting ideal gas state, so that the difference in these salvation free energies, then if I take the difference, okay, the ideal gas reference state value cancels out, and it's just equal to the transfer free energy in taking my solute from, say, solvent 2 relative to solvent 1. Okay, so differences in salvation free energies, as long as it's the same solute in the same form. Okay, so by same form, it's not a tautomer or isomer of that given solute. So if it's the same species, okay, I can take differences in salvation free energies, and that's related to a transfer free energy, which I can relate to a partition coefficient, or essentially a relative solubility. But yeah, so because this is a picture we'll come back to tomorrow when we talk more about applications or use of salvation free energy calculation.